Alright, so in our last class, we had talked about our covalent bonding. So today we are going to go ahead and we are going to take a look at the shapes of molecules. Now, you asked me in the last class that Miss Bond, like how can they have different shapes? So let's talk about it. How can different molecules have different shapes? To understand this, we have to understand a certain theory. Okay? That theory is known as electron pair repulsion theory. Simply put, all electrons are always repelling each other, right? Now, I don't know if you've ever wondered this or not, but in an atom, we have a lot of electrons that are present. We need it to be so the electrons, right? They basically need to arrange themselves in such a way that there is minimum possible repulsion between them. Idea that I always give my students whenever I'm teaching them about electron pair repulsion is that imagine that you're throwing a dinner and the people you have invited do not like each other. So you have to arrange the seating in such a way that there is minimum repulsion or minimum fights between them. Okay, just like you would, so you would try to arrange them. You have one dinner table, you have to fit them all around a table. So you will try to arrange the seats in such a way that there is as little interaction between them as possible, so they do not fight. So similarly, the electrons in a molecule, right? Because in a molecule, we don't just have individual electrons. We have shared pair of electrons, we have lone pair of electrons, all of that. So the electrons will want to arrange themselves in such a way that there is minimum repulsion between them. So based on the number of lone pairs, based on the number of bonded pairs of electrons, based on the number of, your shared pair of electrons, the, the electrons, right, they are going to develop different shapes. So if one molecule has a lot of shared pair of electrons compared to another molecule, that will be a different shape. Now, when we are talking about the shapes of molecules, okay, so over here, I just told you that they'll want to arrange themselves in such a way that there is minimum repulsion between them. Okay, now there is an order to the repulsion. Let me explain to you what the order to the repulsion is. So the order is this. The repulsion between two lone pairs is the strongest. Okay. Lone pair to lone pair repulsion is the strongest. It is the greatest. The greatest amount of repulsion is seen between two lone pairs. Then, between a lone pair and between a shared pair of electrons. Okay? Between a lone pair and a shared pair of electrons. So, instead of saying shared, we use the term bonded. Okay? So, bonded pair simply means shared pair of electrons. Between a lone pair of electrons and a bonded pair of electrons, the repulsion is moderate. And the repulsion between two bond pairs is minimum. What does this mean? This means that, for example, I have a molecule of water. Okay. So if I draw the dot and cross diagram for water, so we will get something like this. Oops. One second.
Miss bonded means it has no free electrons, right?
No, no, bonded is the shared pair of electrons.
It has no free electrons, like it's all of them are bonded. All of them,
Yeah, if all of them are bonded, then it doesn't have any lone pairs. Then all of
yeah,
them are bonded
like
pairs.
no lone. Okay.
Yeah. Okay. So now let's draw a molecule of water. Okay. So a molecule of water will, if I draw the dotted cross diagram, you will get something like this.
There's six electrons and then two of hydrogen.
One second. Yeah. Right? So over here, the repulsion between two lone pairs of electron is going to be the greatest. The greatest repulsion is going to be between the two lone pair of electrons. Then the repulsion between the lone pairs and the bonded pair of electrons is lesser. And the repulsion between two bonded pairs is the least. So the electrons will always arrange themselves in such a way that the repulsion between them is minimum. Meaning that the lone pair, in the example in a water molecule, the lone pair of electrons try to be as far away from each other as possible. The bonded pair of electrons do not necessarily need to be that far because they do not experience that much repulsion anyway. Okay, so this is your electron pair repulsion theory, that all the electrons in a molecule, not in an atom, in a molecule, will arrange themselves in such a way that there is minimum repulsion between them. So now, for example, in a molecule of water, they will arrange themselves in this specific shape. This shape is known as a V shape. I will teach you about all the shapes in just 1 second. But this shape is known as what? It is known as a V shape. And the angle between our shared pair of electrons is 104.5. So you can basically see now, you can understand, right? That this is what I mean, that they will arrange themselves in such a way that the repulsion is minimum. And maximum repulsion is between two lone pairs, and two bonded pairs experience minimum repulsion.
Wait, so
So,
miss, if we had
yeah,
an lone oxygen atom, the
yeah.
two lone pairs, will that have maximum repulsion, or are you trying to say that? Or
Sorry.
like, miss, can you give an example of lone pair and lone pair having the maximum repulsion, like an
Over
atom?
here, even in oxygen, look, even in oxygen, the lone pairs, I've drawn them really far away from each other, right?
Okay,
Like the reason the lone pairs are so far away from each other is because they have a lot of repulsion. So they will want to
okay.
be as far away from each other as possible. The bonded pairs, they do not have that much repulsion, so they can still be somewhat closer to each other. So the molecule over here of water arranges itself in such a way that the lone pairs are far apart from each other, but the bonded pairs are not that far apart. And if we look at the shape of the molecule, so the shape of the molecule over here is a V shape, right? It's a V-shaped molecule. And the angle over here between the two bonded pairs is 104.5. If you measure this angle is 104.5 degrees. Okay? Now, you might be wondering, how am I supposed to know what will be the shape of the molecule? How am I supposed to know what will be the bond angle? So, good thing for you is that we can figure out the shape of the molecule by simply looking at the number of lone pairs and number of bonded pairs. Okay, I'm going to go ahead and make a table for you. In that table, I'm going to discuss with you, I'm going to tell you that if this is the lone pair and this is the bonded pair, then this is the shape of the molecule that we will have. Okay, you basically just need to learn that table. All right, so our columns are like so. On column number 1, we have our number of lone pairs. In column number 2, we have number of bonded pairs. Then in column 3, we have the shape of the molecule. On column 4, we are going to write down the angle. Column number 5 is going to include a dot and cross diagram so we can actually understand as best as possible what the shape of the molecules looks like. You will be given questions where they will give you a molecule and they will say, please tell what is going to be the shape of the molecule, what is going to be the angle between the bonds. So please remember that you can always figure out the shape of the molecules by looking at the number of lone pairs and bonded pairs. So this is a table that you want to learn. Let's start with having just two. One second, Aram, just 1 second. All right. Okay, so let's say that we have a molecule that has two bonded pair of electrons and the lone pair of electrons are zero. So we have a molecule that has no lone pair of electrons whatsoever, but it has two bonded pair of electrons, right? An example of this that I can give you is carbon dioxide. Okay, in carbon dioxide, we have something like this. We have something like this. This is my carbon 1, 2, 3, 4. Then I have oxygen. Oxygen over here, oxygen over here. 1, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay. This is what the top cost diagram for carbon dioxide is going to look like. A carbon dioxide gas has two double covalent bonds. Okay. So with both of the oxygen, carbon is going to make a double covalent bond. Now over here, technically speaking, Arham, you might say, Miss, but the total number of shared pair of electrons are 4. You would be right that the shared pair of electrons that the total number of electrons that are being shared are 4. Okay, but this is one bond. This is one bond, and this is the second bond. So this is one pair of electron, and this is another pair of electrons. Okay, this is how we consider
Okay.
it to be a pair. So this is one pair of
One second,
electrons.
miss.
Yes,
Miss, for the electrons, the other electrons which are not bonded on oxygen, shouldn't it be on the opposite side because they
no,
have the most
because it is
repulsion?
the okay. So we are only concerned with the lone pairs or bonded pairs around the central atom. Okay, I should actually mention that. Let me add that to the definition. Thank you for bringing that point up, right? So the electrons in a molecule will arrange themselves around the central atom. We are not concerned with the other atoms in the molecule. It's the central atom which is important. Okay, so when we are going to be looking at the number of your lone pairs and number of bonded pairs, I am always talking about the central atom. I am not talking about the atoms on the side. Okay, so this theory specifically applies to the molecule that is at the center of the atom. So in this case, that's oxygen. Okay, so oxygen is our central atom. So it has no lone pairs, but it has two bonded pair of electrons. So whenever you will have no lone pairs and two bonded pair of electrons, the shape is going to be considered as linear. The shape is considered as linear, and your bond angle is always going to be 180. Okay, so the angle over here is going to be 180.
Linear
Then,
means horizontal, right?
yes, because there's no lone pair. See, so in this case, there's no lone pair, right? So the bonded pair of electrons can be on completely opposite sides with each other, right? If there were lone pair presence, they would not be able to do that. Why? Because then the lone pairs would try to be as far away as they possibly could, right? Like I gave you the example, imagine that you're hosting a dinner for a bunch of people who do not like each other. Some people absolutely hate each other. Some people, they don't like each other, but they're also not, that against each other. So the people
Okay.
who are they completely hate each other, you will try to put them on opposite sides or at least as far away as you can. People who only dislike each other a little bit, you can sort of accommodate them and maybe they can be a bit closer to each other. Same thing over here with electrons. Lone pairs want to be as far away from each other as they can. Bonded pairs are somewhat okay being being as close as possible. So in this case, we didn't have any lone pairs. So the bonded pairs can be as far away as they want to be. That is the main thing, that they will always want minimum possible repulsion. So if they have the choice of being on complete opposite sides, there are no lone pairs in the middle, so they will be on complete opposite sides. This is known as a linear shape. Then our next shape that we are going to have is that we can have the shape where again the lone pair of electrons are still 0. We're not taking any lone pairs into account, but the bonded pair of electrons are now 3. An example that I can give you of this is boron tetrichloride. Okay, boron trichloride or boron trifluoride. Boron is in group 3. So it has got 3 electrons in its option. it will be bonded to chlorine. Okay. Now, in this case, Arham, you might wonder and you might say to me, Miss, that if you draw the dot and cross diagram, that you just draw the dot and cross diagram. So if I draw your dot and cross diagram, you can clearly see that boron is not getting a complete outer shell, right? So you might ask me,
Yeah.
Miss, how does that work? So the outer shell concept, you need to realize that now at an A level, you can understand that there are exceptions to it. There are a few situations in which the molecule will not have a complete outer shell. Okay. One of the example of this is boron trichloride or boron trifluoride. This is one of the examples. In boron trichloride or boron trifluoride, we do not see a complete outer shell. So there are going to be a few times where you're going to have exceptions to the octet rule, where the molecule will not be following the octet rule. So
And miss,
one of the
sometimes it will
examples,
be also greater than, right?
sorry,
Sometimes it can be greater like than 8
yes,
and it can
sometimes
be
it can
less
also be
than
greater
1.
than it. Yes, it can be greater than it as well. So this shape is known as trigonal plan. Trigonal why? Because obviously you can see it's in a triangular shape, and trigonal planet. Why do we say planet? We say planet because all of them are in one plane. Okay. You can see even if I draw the molecule for you in terms of the bonds, so the bonds are going to be like this. Actually, right? And in this case, the bond angle for trigonal planar is, I don't think we need to learn the bond angle for trigonal planar. All right, I'll tell you. It's fine, I'll still tell you. It's 120 degrees. All right, now let's continue. Next option that we can have is that we can have the next option that we can have is we can have a molecule that has 4 bonded pair of electrons and no lone pairs, but we have 4 bonded pairs. A very good example of this is methane. Okay, in methane we have H4. So if I draw for you the structure of methane, I will draw it like this.
Miss, you have to memorize the angles and names, right? Because they don't make sense.
Yes. No, this is not something that you can figure out just by looking at the molecule, right? Like there is no way that you can just look at the molecule atom and you will know what shape it is. So you will have to learn that if I have this many bond angles, then this is the shape and this is, okay?
Okay.
This is a lot of learning, this chapter, shapes of molecules.
Miss?
Yes, sir.
Miss, is it possible if you could like again explain in a little detail like a lone pair and lone pair and lone pair and bonded pair?
Yeah, sure, Arun. Okay, now look over here. Do you see that when I'm making this shape now, see how I'm making this dotted line and the triangle? The reason I'm making this dotted line and the triangle is that to show the three-dimensional structure of the molecule. Okay, so that's what I told you, that these molecules are three-dimensional in structure. So over here, now it normally does not matter which one you show with a triangle, which one you show with a dotted line. The examiners don't care, okay? It's just that
Okay.
one bond should have a triangle and one bond should be a dotted line. Okay, why? Because you want to show the examiners that you know that now this is a three-dimensional molecule. So it's not just going to be arranged in one plane in y-axis or x-axis. It's also going to be arranged diagonally in the z-axis. This shape is known as tetrahedron. This shape is known as tetrahedron. And the bond angle that we see between tetrahedral is 109.5. Now over here, now look, we don't have any lone pair of electrons, we only have bonded pair of electrons. Since we had four bonded pair of electrons, they have all arranged themselves equally. The angle between all of the bonds, all of the bonded pair of electrons is going to be 109.5, right? So this is basically what is happening, that the electrons will always want to arrange themselves in such a way that there is minimum repulsion between them. So in this case, they all arrange themselves in such a way that they are all 109 degrees apart from each other. So they're equally spaced. Yes, sir.
Sorry, Miss, can I take methane as like, since it's tetrahedral, can I like think of it as a shape of diamond?
Sure, I guess.
I mean, so Miss, like I can like relate it with diamond so it's easier to remember.
Yeah, sure. If you want to, if it makes it easier to remember, sure, you can do that.
Okay.
Okay, then the next option that we can have is we have five lone pair, still have zero lone pair of electrons, but we have five bonded pair of electrons. Okay, now in five bonded pair of electrons that we have, so a good example that we can take of this is PCl5, phosphorus chloride, phosphorus 5 chloride. Okay, phosphorus can have two charges, +5 and +3. So this is phosphorus 5 chloride. So if we draw the dot and cross diagram, this is what it will look like. 1, 2, 3, 4, 5. Right? So over here you can see that phosphorus clearly has 10 electrons, right? In its outer shell. Does not have 8 electrons, it is 10 electrons. So that's what I was saying, that there are exceptions to the rule. That an molecule can have, or an atom can have more than 8 electrons in its shell, which you and I know makes sense because shell number 3 can have up to 18 electrons. It can also have less than 8 number of shells, 8 number of electrons. If you draw the shape of the shape of the molecule is going to be like this. This shape, where we have 5 bonded pair of electrons, this shape is known as trigonal bipyramidal. The way I remember it is like this, that it is trigonal bipyramidal. This is now this is just how I learned it. Okay, this is not, I'm not saying that this is the theory behind it. This is just how I learned it. That I thought of it this way, that it has a triangular. If you look into it, it has two triangular pyramids. You know how like with pyramids, we can have pyramids that have a triangular base and we can have pyramids that have a square base. So
Yes.
I just thought of it this way, that we are getting two triangular pyramids. So that's how I learned it. That this is one triangular pyramid. This is the over here the second triangular pyramid. So that's how I learned it, that this is trigonal bipyramidal. Bi means two, and I just learned of it this way, that there are two triangular pyramids over here. That's just how I
Mhm.
learned it. That's not the theory behind it. That's just my trick for remembering it. Trigonal bipyramidal has the bond angle between 90 to 120. So somewhere over here, like over here, it has 90 degrees. Over here, it has 120 degrees. Like this. Okay. After trigonal 5 lone pair of electrons, the next possibility that we can have is we can have 6 bonded pair of electrons. So once again, the lone pair of electrons are 0. We have 6 bonded pair of electrons. 6 bonded pair of electrons are seen in a molecule that is, excuse me, okay. The next one, so we can have 6 bonded pair of electrons in a molecule known as sulfur hexafluoride. Sulfur has 6 electrons, so 1, 2, 3, 4, 5, 6. And it's often bonded with fluorine. Right? So in sulfur hexafluoride, you are going to have what? You are going to have 6 bonded pair of electrons. When you're drawing the shape of the molecule, this is how we draw it. You can just learn all of this. By the way, that's what I did when I was a big exam. Right? This shape is known as octahedral. Oct means Oct
Eight, right?
means 8, right?
Eight.
So the reason it is 8 is because if we join all of these together, so we will get an octahedral. That's how. Okay, so we will get 1, 2, 3, 4, 5, 6, right? So we end up getting not exactly an octahedral, but we get like an octahedral shape. So that's how I learned that this is an octahedral. And the bond angle that we see with octahedral, once again, it varies. It is somewhere between 90 and 180. Okay. Then, now let's talk about what if we have lone pair of electrons. So if I have one lone pair of electrons and I have one bonded pair of electrons. This is an example that you probably already know. What is this an example of? Ammonia. In ammonia, I have two lone pairs and two bonded pairs. Sorry, one lone pair and one bonded pair. Right? Now, in this case, I have noticed something interesting. Right? You will see that the bonded pair of electrons are close to each other, but they are very far away from the lone pair of electrons. Why? Because the repulsion between the lone pair of electrons and bonded pair of electrons is moderate. The
But miss,
greatest
that is
amount of,
lone pair and bonded? That is lone
yes,
pair and bonded or just bonded and bonded?
uh, uh, the greatest amount of repulsion is between two lone pairs.
Lone. Yes.
Then moderate repulsion is between one lone pair and one bonded pair, and two bonded pairs have the least amount of repulsion. So the most amount of repulsion is between these two, right? Do you see? They are
Yeah.
as far away from each other as possible. The bonded pairs are not that far away from each other. That's because they don't repel each other that much. But they have moderate repulsion with the lone pair of electrons. So they're very far away from the lone pair of electrons. That's the concept, right? That's the basic concept. That whenever you will, so far, if you look over here, you can see that when you didn't have any lone pair of electrons, when all you had were bonded pair of electrons. So they always arrange themselves equidistant, right? No one is too far away from each other. If there were only two, they just went over on the opposite side. If there were three, they said, you know what, let's just equally divide up into three. If there were four, they said, once again, let's just take four areas. If there were five, so far, the distance between them was somewhat equal. Now, over here, when I moved on to your ammonia, now you notice that even if you just look at the diagram, even if you don't look at anything else, and you just look at the diagram, you will notice this, that the bonded pair of electrons are far away from the lone pair of electrons. That is because they experience greater repulsion with the lone pair of electrons. That is electron pair repulsion theory. That electrons will always arrange themselves in such a way that there is minimum repulsion between them. So think of it this way, that you have invited three people to dinner. Okay? There is one person that everybody hates, and the other two people, they do not like each other, but they're also, not that, they don't mind each other that much. So what will happen, that the person they hate is going to be, you're gonna want to keep him as far away as possible. The other two, again, you want to keep them at a distance, but they can be somewhat closer to each other because they are not that much on bad terms, right? So
Yes.
so that's the entire concept, that you want to arrange the electrons in such a way that there is minimum repulsion between them. So if there's a lot of repulsion between lone pairs, then keep the lone pairs far away, right? And this sort of a shape is known as your, one second.
But miss, how does bonded and bonded look like? Because this in this nitrogen and hydrogen, the one which is furthest away, I can tell that that's a lone pair, and the one that is on the other side are both like lone pair and bonded pair. But what does bonded and bonded pair look like?
This shape is known as trigonal pyramid. Okay. This is
Yes.
different than the one I taught you before. Okay. Before that, I taught you trigonal bipyramidal.
Bipyramid,
This
yeah.
is, yeah, this is trigonal pyramidal, not bipyramidal, just trigonal pyramidal. And if I ask you the shape of the molecule, the shape of the molecule is going to look like this. This is the lone pair of electrons over here. Oh, two, three, four. I did not draw the dot and cross diagram correctly. One second. Nitrogen has 5 pair of electrons, I forgot. This is the structure of ammonia. I made it incorrectly. Anyway, so over here, the bonding is going to look like this. Okay. And for trigonal pyramidal, the angle that we have is also 109.5. Then let's go on to what will happen if we have two lone pair of electrons. If we have two lone pair of electrons, so You have two lone pair of electrons and two bonded pair of electrons. The example of this is something that I have already given you, by the way, oxygen and hydrogen making bond. So now over here, you can see that in the water molecule, we have got two lone pair of electrons. So these lone pair of electrons are the molecule is going to arrange itself in such a way, the molecule will try to arrange itself in such a way that the lone pair of electrons is as far away from each other as it possibly can be. Okay. Again, the lone pair of electrons cannot just go on opposite sides because the bonded pair of electrons are also present. And yes, they might not have too much repulsion, but they still have some repulsion, right? So lone pairs are going to be as far away from each other as possible. As possible is the keyword. Okay. And the bonded pair of electrons is, once again, it's not too far away from each other. They're somewhat close to each other, but they will still have some separation between them due to repulsion. This is how it is going to look like if we have two lone pair of electrons. And this is going to lead to what we call as a V shape or a bend shape. Okay, this is a V shape or a bend shape. And the bond angle that we have is 104 point. So this is what we need to know regarding the shapes of the molecules. You should be able to predict what is going to be the shape of the molecule simply by looking at what? Simply by looking at the number of bonded pairs and number of lone pairs. Okay. One thing that I always tell my students is just to basically learn this table. Okay. So in this particular case, what is going to happen that so in this particular case, what is going to happen that you will be given questions where they will ask you, give you a molecule, and they will say, okay, please tell us what is going to be, the shape of the molecule and what is going to be the angle. So you are not to get worried, you just have to learn this table. You will simply draw the dot and cross diagram and then check the number of pairs around the central atom. Do not concern yourself with the entire molecule. Sometimes they will give you a huge molecule and they will ask you about only one specific bond. Right? They'll give you a huge molecule and they will say, oh, can you tell us the bond between sulfur and chlorine? So sulfur is so in that case, all you have to do is identify the central atom. Then all you have to do is draw your dot and cross diagram. Draw your dot and cross diagram, figure out the number of bonded pairs and number of lone pairs. And once you have done that, you will simply remember the shape and the angle of the shape. Along with that, you should know how to draw your dot and cross diagrams and also how to draw how to show all the bonds as well. Okay. And in the bonds, what do you have to remember? You basically have to remember this, that these bonds are three-dimensional. So one should be represented with a dotted line, one should be represented with a shaded triangle. And you should know about electron pair repulsion theory. That's what they're going to ask you about. Why is the molecule arranging itself in this way? So you will explain it using electron pair repulsion theory. Now keep in mind, if the examiners say, why are the molecules arranging themselves in this way? You don't need to give a detailed answer that, oh, there is a lone pair of electrons and they will be as far away and then we will have this. Just write down the theory. That's it. Okay, that the electrons will arrange themselves in such a way that that there is minimum repulsion between them. That's it. No need to ever give any explanation. Okay, and okay, one second. Let me check your syllabus to make sure I didn't miss anything in the topic. All right, so this is all you need to know related to your shapes of the molecule. Now, what is the next thing that we have to know related to our covalent bonding? The next thing that we have to know related to our covalent bonding is intermolecular forces. Okay, I'm just going to give you an introduction to intermolecular forces right now because we don't have the time to actually start the topic. So I'm going to give you an introduction and then we will continue the topic in the next class. I'll tell you properly. But basically in intermolecular forces, so far in your IGCSE, whenever we talk about gases or anything like that, we would just say, oh, there are weak intermolecular forces of attraction, right? That would be your answer. That there are weak intermolecular forces of attraction in gases. Now, the question that comes is, you will study what are the weak intermolecular forces. If we have van der Waals forces, what actually are van der Waals forces, right? So we are going to study about three types of forces. One is van der Waals forces, one is permanent dipole to dipole forces, and then we will study about hydrogen bonding, right? And when
Okay.
we study the concept of these forces, right? So a lot of the things are going to make sense that did not make sense before. For example, talking about the trend in boiling point. Okay, talking specifically, we have to understand that if we talk about the boiling point of your hydrogen halides, okay, the boiling point of hydrogen halides follows a very certain trend. So we can understand that trend by, just give me 1 second. So we need to understand this trend by we can understand this trend by once again looking at the forces that we have between ionic compounds. So we have hydrogen bondings, we have van der Waals forces, and we have what? We have our permanent dipole interactions. Now, when we talk about our for us to understand for us to understand the concept of our intermolecular forces, we first have to understand a concept of electronegativity. What is electronegativity? Electronegativity is the ability of an atom to attract a shared pair of electrons towards itself. Okay? Every single atom in the periodic table has an ability to attract the shared pair of electrons towards itself. Meaning that let's say we have a molecule of hydrogen chloride. Okay. Now, chlorine has high electronegativity. What does that mean? That means that chlorine can attract the shared pair of electrons towards itself. Now, keep in mind that chlorine is not taking the shared pair of electrons. Chlorine is not getting the shared pair of electrons. It's not taking it away from them. The shared pair of electrons is still being shared between hydrogen and chlorine. It's just that chlorine will pull it towards itself. Okay, that's one concept I want to clarify. That we are not pulling the sorry, we are not breaking the covalent bond. It's not that chlorine will take both of the electrons for itself. Okay, that will not happen. What is going to happen is this, that the same shared pair of electrons still being shared between hydrogen and chlorine, it is going to be attracted towards chlorine. Chlorine will just pull it closer. Okay, sort of like if two kids are playing with toys, they're still sharing the toys, but one kid has pulled them a bit closer. Same concept. Now, since chlorine would have attracted the shared pair of electrons towards itself, right? Since it would have pulled those electrons towards itself, it will end up getting a small negative charge. Okay? Hydrogen will end up getting a small positive charge. Why? Because the electrons still being shared between hydrogen and chlorine, but they are a bit more attracted towards chlorine now. We call this a partial charge. Okay? Chlorine becomes partial negative, hydrogen becomes partial positive. This is known as a dipole. In a molecule, when one atom becomes positive partial and one atom becomes negative partial, we say that the molecule has a dipole. Or instead of molecule having a dipole, we say that the bond has a dipole. Okay? Now, the dipole, this partial positive charge and partial negative charge is why we will have forces of attraction between the molecules. But these forces of attractions are weak. Why? Because these charges are partial and not permanent. In ionic compounds, we have a permanent positive charge, permanent negative charge. Over here, the charge is partial. If the electrons are, if hydrogen, for example, ends up attracting the electrons towards itself, it will end up becoming negative. So these are partial charges. They're not fixed. They are simply happening due to fluctuation of the electrons. The electron are fluctuating, can fluctuate between two atoms, and that can lead to a dipole, and that dipole can lead to your uh, molecules developing attractions for each other. But since these charges are, like I said, partial, so the forces of attractions are not that strong. And since the forces of attraction are not that strong, that's why we call them weak forces of attraction. So over here, we have to study about three types of forces. We have to study about bondable forces. Bondable forces are seen in those molecules that have the same electronegativity. So for example, bromine, okay? In a molecule of bromine, both the atoms are made of bromine, right? So they will both have the same electronegativity. They have the same ability to pull the pair of electrons towards themselves. Then we have permanent dipoles. Permanent dipoles are seen when you have two atoms, okay, in a molecule, and one has high electronegativity and one has low electronegativity. So one is able to pull the electrons towards itself. Then the third we have is hydrogen bonding. Hydrogen bonding happens in a very specific conditions and a very specific requirement for it. Okay, so we will go ahead and take a look into detail regarding all of this in our next class. All right.
Okay, miss, sure.
Okay. All right. Okay, Aram. By the way, I hope this topic, the shapes of molecules, is all clear. Right? No confusion in this.
No, miss.
Okay, great. So we will stop it over here for today, and we will continue with our topic in the next class then. Okay, Aram?